Alright. So guys, here's the second derivative test. Okay, so if your function, if the first derivative is 0, and you can take the second derivative, if the first derivative is 0 and the second derivative is positive, then you have a relative minimum. If the first derivative is 0 and the second derivative is negative, you have a maximum. Now, if the second derivative is positive, that means it's concave up, right?
Right.
If I draw something concave up that changes direction, if I have a horizontal tangent line there, that has to be a minimum. Right? If the first derivative is 0 and the second derivative is negative, when the second derivative is negative, it's concave down. If I draw something concave down, and I draw a horizontal tangent line there, that's a maximum. So that's what this is saying. If the first derivative is 0 and the second derivative is positive, you have a minimum. You have a lowest point. First derivative is 0, second derivative is negative, you have a maximum. Just another way of checking if you have a maximum or a minimum. Right there. All right, then what we're going to try to do here is put everything together. This is going to be fun right now. We're going to find the intercepts, extrema, points of inflection.
All of that.
Yeah, list where the graph's increasing or decreasing, list where the graph's concave up or concave down, and then sketch the graph. So, Joss and I decided, you know, there's no sense complaining, we might as well just get to work.
It's usually the case in life.
Is it? So, if we want to find the intercepts, first thing Jocelyn and I are noticing, we get the natural log of x. Right? That tells us x always has to be greater than 0. Right? You can't take the natural log of 0 or a negative number. So we can sort of refine our graph. We know it's going to be like that. The graph's always going to be to the right of the y-axis. Right? Which also tells us there's no y-intercept. Right? So we can't put 0 in for x. So then to find the x-intercepts, we'll take the function and set it equal to 0. Take 1/2 x squared minus the natural log of x. Set that equal to 0. How would we? I don't even know how to solve that for x. Huh?
You need to skip all the problems.
How would we do it?
I don't know.
I'm just looking at it.
Do it. I surely can't tell you how to do it.
So you know what I think we'll do? We'll skip that for a minute. We'll go to find the extrema. To find the extrema, that's where the first derivative is 0 or undefined. So we'll do the first derivative. So the derivative of 1/2 x squared would be 2 times 1/2, which is 1x, minus the derivative of natural log of x is 1 over x. Now, that's undefined when x is 0, but we can't have x equal to 0. So then we'll set it equal to 0 and solve for x. So if I bring the 1 over x over, I'll get x equals 1 over x. Cross multiply, I'll get x squared is 1. So x is going to be plus or minus 1. Now, we could throw out the negative 1, right? Because we're only dealing with numbers greater than 0. So if we got to be greater than 0, we can go to 1, and then 1 to infinity. Let's check that in the first derivative. So a number less than 1, say 1/2. If we come back to this right here, here was our first derivative. If I do 1/2 minus 1 over 1/2, 1 divided by 1/2 is 2. So 1/2 minus 2 is negative. Something bigger than 1, I could pick 2. I get 2 minus 1/2, that's positive. So it's increasing, then decreasing. Or backwards, decreasing, then increasing. Right? So that's telling us there's a relative minimum at x equals 1. Alright, so if I put 1 in for x back in the original function, I get 1/2 minus the natural log of 1 is 0, so I just get 1/2. So at 1 and 1/2, there's a minimum. You'll say that's 1 and that's 1/2. there's a relative minimum right there. Now, if that's a minimum from this second derivative test, I know this has also got to be concave up right there. Shoot. I'm going to wait to sketch that. I'm thinking to myself, this is concave up. It's probably going to go up like this. Asymptote like that and do something. Now let's do the second derivative to find its concavity. So the first derivative was x minus 1 over x. So the derivative of x is 1 minus, what's the derivative of 1 over x? Yeah, so see, Casey was thinking 1 over x is x to the negative 1. So you have negative 1 times x to the negative 2. So this is going to be 1 plus 1 over x squared. Undefined when x is 0, but we're only dealing with x is greater than 0. If we set this equal to 0, I don't think there's ever a solution, is there? Right, 1 plus 1 over x can never equal 0, because x squared is always positive. So this has no solution. But if the second derivative is 1 plus 1 over x squared, that's always greater than 0, isn't it? Any number we put in for x that's greater than 0, that tells us this graph is always concave up. The graph decreases from negative 0 to negative 1, increases from 1 to infinity. And notice too, the first derivative was 0 at 1, and the second derivative was positive. If the first derivative is 0, second derivative is positive, it's concave up. So this graph has to come over here, go up like this, like it's going to be decreasing down here, concave up, and then it's going to increase, be concave up. So it should look something like that. And look, we went back to the original thing trying to find the X intercepts. There is no X intercept.
Where's the extrema?
There's right here at 1/1/2. That's a relative minimum. We had a relative minimum of x equals negative 1. Let's just check that with the calculator. Think of a graphing calculator? They did.
No, why did they think of this math?
Because look at that.